I welcome you to my today's talk on digital technologies for integrated crop protection. My name is Anne-Katrin Mahlein and I'm a researcher at the Institute of Sugar Beet Research, and it's really an honor today for me to provide you within the next 20 minutes new insights in our research within the frame of Phenorop. Plant diseases and crop protection are elementary for crop production. However, there are significant changes are necessary to transform practices for sustainable futures. The reasons for that are manifold. For example, the political framework and societal demands are changing. The European Green Deal strategy paper, as an example, envisaged a 50% reduction in plant protection products used by 2030, in addition to an increase in organic farming and a reduction in fertilizers. Additionally, there is a loss of active ingredients available for the farmers due to expiry of approvals and a loss of efficacy of plant protection compounds due to resistance of the pathogens. In parallel, we observe dynamic changes in the pathogen spectrum, and also effects of climate change impact the occurrence and damaging potential of pests and diseases. Therefore, we need a consistent implementation of integrated pest management tools, and additionally, innovative approaches are demanded to develop alternative methods and control mechanisms. At this point, the integration of digital technologies for a knowledge-based and sustainable plant protection is one part of the puzzle. Visualized on this slide is a simplified way and a vision of a database disease management. You go into your field, take a picture by a drone with an RGB camera, a multispectral camera, or a hyperspectral camera. This can be on a drone, as mentioned, or on a robot, or with a tractor-mounted systems. This data is analyzed by machine learning or deep learning, and the information on the presence of a plant disease is georeferenced in a distribution map. And this can be the basis to create an application map which can autonomously guide a spraying system or another tool to control a disease. But of course, it is not that simple. To reach this pipeline, we need an interdisciplinary approach, integrating complementary disciplines such as agronomy, phytopathology, artificial intelligence, sensor technologies, and geoinformatics. Finally, the information from an automated disease detection and severity measurement can be used for smart crop protection or in plant breeding to speed up the screening process for resistant or tolerant varieties. Crucial for the use of sensors for plant disease detection or for characterization of pathogens are the optical properties of plants during plant-pathogen interaction. On the left side of the slide, a schematic cross-section of a leaf is visualized. Incoming light is parted in different ways. One part of the light goes through the leaf, which is called the transmission. One part of the light is absorbed, depending on the pigment content and other biochemicals within the leaf. And what we are able to measure consists of the internal reflectance after diverse scattering processes and the direct reflectance from the surface. So this is the situation of a healthy plant, but now imagine a plant is diseased with different pathogens like yellow rust or brown rust or septoria. Then individual changes of the plant structure and the biochemical and biophysical compositions appear, and we make use of this effect to identify and characterize the different diseases based on sensor data, as an example, like hyperspectral data. Hyperspectral data or multispectral data are adequate formats with a lot of information for observing disease plants and for utilizing optical aspects of the pathogenesis. But how are hyperspectral data composed? We have a three-dimensional data cube with two spatial dimensions, and additionally we obtain a spectral dimension here in the spectral axis. So with each image pixel, we obtain an entire spectral reflectance curve in the visible and in the near-infrared range, and sometimes even in the shortwave infrared range. And for each pixel, we obtain the information of a spectral signature, and this significantly changes depending on the health status of the object. For example, if the leaf is healthy or if the leaf is diseased. How can we transfer this theoretical background now into a relevant application? And we start with an application scenario of diseases in wheat. And the final aim is an in-field disease detection as well as a yield monitoring. But today we focus on the detection of different diseases, and I brought you some examples for the detection of brown rust and yellow rust based on hyperspectral data. On this slide, characteristic spectral curves of brown rust caused by Puccinia triticina on wheat leaves is visualized. Within the study of Bohnenkamp et al., a library of hyperspectral signatures of relevant foliar diseases of wheat was established. As you can see here, the spectral signatures differ depending on the date after inoculation. First symptoms appeared 4 days after inoculation, and on that time point also reflectance in the visible range changed significantly. At later time points, also a change in the near-infrared plateau was observed and a steady increase of reflectance in the short-wave infrared. When analyzing the time series measurement of brown rust diseased wheat leaves in detail, time-independent turning points of pathogenesis could be observed. These vary in the blue range between 4 and 7 days after inoculation, at the green peak, and around 600 nanometers as well at the near-infrared plateau. These turning points can be used to identify infection procedures in the field without knowledge on the primary infection time point. But the remaining question is how to get into practical use. So hyperspectral imaging is rather cost-intensive. It demands complex measuring setups, and the data analysis and data handling is very complex and time-consuming. In very short time, you obtain terabytes of data which needs to be analyzed and interpreted in an adequate way. And therefore, one of our research questions is, do we need hyperspectral sensors in the field, or can we reduce the data complexity? What is the spatial resolution we need for sufficient accuracy and sensitivity when we aim to detect symptoms of diseases in a sub-millimeter range? And what are approaches to reduce the data and to select most relevant wavelengths which can be used as a first step for defining and identifying sensitive sensors which are very specifically tailored for a specific situation? This approach was followed in a field study where a hyperspectral camera was mounted on a UAV platform and in parallel on a ground-based vehicle. The spectral signatures were processed by a feature selection algorithm which provides the number of relevant features for disease detection and the 10 most relevant spectral wavelengths which were necessary for the detection of diseases within the field. And this step was performed individually for each disease of wheat, and here the example of yellow rust was indicated. And by this we have a data basis for creating application maps which can be used as an information for a practical farmer for performing plant protection measurements. But we have to know that there are several challenges when we aim to assess diseases in the field and in complex canopies such as cereal canopies, as it is in the case of wheat. Looking at the canopy from above, a mixture of information and complex structures of young leaves, of older leaves, of ears, of senescent part, of shadows and mirroring effects and diseases at different stages occurs. So the algorithms we apply needs to be able to handle this complexity, and simple algorithms like spectral angle mapper, a very old algorithm from remote sensing, is not able to provide sufficient results, but other simple machine learning approaches like support vector machines are more suitable to handle this kind of complexity. Another approach to address this challenge are data-driven analysis. And to test the potential of data-driven analysis like SIVM and classification, we prepared a screening scenario on the canopy level from greenhouse data. The experiments were performed at mini-plot facilities at the campus Klein-Altendorf, and in the mini-plots, 6 different barley varieties with differing susceptibilities against Plumeria graminis forma specialis hordi were cultivated and inoculated with the pathogen. And then we observed the development of the characteristic powdery mildew pustus and screened it with an automated sensor platform. And this automated sensor platform was equipped with a hyperspectral camera and an illumination system to obtain time series data with high quality. And as you can see here in the data is very complex with shadowing, it's heterogeneously illuminated, and you see only very, very small symptoms of the disease, like here in this part, and therefore you need a proper algorithm to handle this complexity. And here we applied simplex volume maximization as a valuable approach to handle the complexity. By spanning the simplex across the data cloud, we identified characteristic archetypes and classified all other data points with respect to these archetypes. And the result was very positive. We obtained a disease detection with a high accuracy, and the algorithm was able to handle the complex data structure and the heterogeneous illumination system and situation as well. Yeah, but still until today, the disease detection in the field is a significant challenge and influenced by the scale and the perspective. So the data quality is really crucial on that. And also the resolution and the temporal availability is very important for disease detection. And on this slide, you see UAV multispectral images of an experimental sugar beet trial disease with the Cospora leaf spot. From above, we have again a very complex canopy structure with overlaying leaves, and we see soil as well and other elements in the experimental trial. But when we have a closer look, we can identify individual plots or even single plants. But for the assessment of relevant traits such as disease severity or disease incidence, an even higher level of information may be necessary. And for that, the identification and segmentation of single leaves or individual symptoms is necessary. And this is what we address within FINOROP. We have the PhD thesis and research of Abe Barreto, Facundo Espisuya, and Maurice Günder. And within their research, we made a relevant step forward to categorize fields from UAV data with a high level of information. And this I will present you during the next slides. On the slides, you will get some very recent information about recent developments and results. And what you see here is a multi-temporal tracking of sugar beets with deep learning. Currently, we aim to integrate sensor data and environmental data for prognosis and monitoring of disease development in sugar beets, and therefore Maurice and Facundo established this kind of multi-temporal tracking of sugar beets by a deep learning approach. By this, one is able to monitor each single plant on the field or in a plot from plant emergence over canopy closure until harvest with a very high spatial resolution. So literally each single plant with its location can be tracked and found at any time point, and this can be the basis for the integration of data layers from sensor data. And this sensor data can be, for example, environmental data, it can be data from other sensors, it can be also data from satellites, which can be georeferenced here, and it can also be metadata, like for example data from visual monitoring and rating from a human being. And this is a very important step we made here forward, because now we can really categorize the fields and provide a knowledge-based tracking and information on the situation. The single plant detection and cataloging is the basis for a digital rating of diseases with CNN. And here it is important to track each individual plant over time and to provide a disease severity number for each plant at each single time point, because disease severity is also a dynamic process which will change over the time. So what has been done by Facundo, Maurice and Abel? The data was split by them into test and training data and lit CNN with 3 convolutional layers and 3 linear transformations were applied. And the result is for each individual plant and at each relevant time point, a rating number in accordance to a well-established rating system. And this rating system is the so-called KWS scale. This scale expresses an increase of the disease severity from 0 to 9, whereas 0 indicates no symptoms and healthy sugar beet plants. And this can be now, or this approach can be now applied on the UAV field data at several time points and provide a very detailed and very accurate expression of the disease severity over time. So this approach was applied on an entire data set of our field experiment from 2020. In 2020, we cultivated two different sugar beet varieties with different susceptibility and tolerance against Cercospora. We had differing fungicide regimes, and we had plots which were inoculated with infectious structures and other plots which were not inoculated. The field experiment was monitored with a UAV equipped with a multispectral camera and an RGB camera, and in parallel environmental information was assessed, like spore flight and the temperature within the different plots, and a ground truthing was performed by visual rating by a human expert who evaluated and rated each plot at each observation time point of the drone. On the left side of the slide, you see the RGB orthomosaic images, which are visualized, and on the right side, you see the automated rating of each individual plant in accordance to the KWS scale with the CNN-based approach. So we can now easily observe the first diseased sugar beet plants at the beginning of August in the experiment. You can see it here with the very small red dots, because each dot represents a plant. And what we also see that there are disease clusters which appear at this time point, and later in October these clusters are increasing and we have entire areas which are diseased. But now let's have a closer look on this indicated plot to see the temporal dynamic of the disease severity and disease development of this plot on the next slide. And this is a picture I really like a lot, because we have this single plot visualized as RGB pictures and with the digital rating scale over time from July to October. And we see that at the early time point in vegetation period, we have a very healthy situation in the field. We have no diseased plants, but in August, first diseased plants appear, and the number of diseased plants and the severity of the disease increased over time. And this is a very accurate view on the plot and can serve as the basis, for example, for breeding, for the selection of resistant or tolerant varieties, but it can be also used for practical agriculture. So what will be the next step? We are now able to assess the disease severity, and also the disease incidence, which are very important parameters in plant pathology and for plant protection. The next step, that's our aim, is to integrate data and information from different domains, such a multi-dimensional data integration of optical data, of environmental data, of spore flight data, for example, or the human rating will definitely increase the knowledge on the situation in the field and will support farmers in decision making. And we strongly believe that this will be the future of digital plant protection routines. However, we still need improvement and method development and continuous evaluation of existing prototypes, because most research results are very specific or for a specific host pathogen system, and the transfer of the data from one environment to another environment and from one variety to another variety still needs further research and development. So we need more and improvement of the methods and a continuous evaluation of existing prototypes. And this work is done within our experimental field-side pharma space. And if you're interested in that, you can inform yourself on the homepage or just contact us. Coming to an end of this talk, I would like to express some remaining challenges and research priorities. And of course, this list is far from being complete. It is still an open question how necessary and important an early detection of plant diseases is before symptoms appear, and how accurate a sensor needs to be. So do we need multispectral cameras or hyperspectral cameras? What is the temporal and the spatial resolution we need in an observation? Or are highly resoluted RGB cameras sufficient? And these both questions are, of course, depend on the host pathogen system we observed and on the crop which is investigated. Another open question where we need more research is the consideration of crop geometry on the data and the assessment and the dynamic of growth in the field and other external factors on the data assessment. In plant pathology, we often have or we observe frequently new or invasive plant diseases. And here we have to address the question how digital technologies can support plant health and inspection. What we also see and identify as a research gap is the question of multiple stress, so the interaction of biotic and abiotic stress, and also the investigation of mixed infection, which often occurs in field and under practice. So we definitely do need more research on the topic of multi-stress. When we come to a practical application, there's an open question how spot application of plant protection products like fungicides impact the epidemiology of pathogens and the disease dynamics. So not much is known about that because so far an homogeneous application of the products on the entire field is the normal case. And at the end, we should not forget the farmers and the persons who apply the technologies. And we definitely do need more knowledge transfer and to the end user. And there is still the question of these, whether these systems should be available themselves or if they should be provided as a service through crop management consultants or advisory services. Yeah, and with these questions, I come to the end of my talk, and I thank you very much for your attention, and I'm looking forward to answer your questions.